1 to 1, which is having two different paths, namely path A and path B. 1 to 2 is path A and 2 to 1 is path B. Let there be a heat supply of Q1 to 2 of amount, say 100 kilojoules supplied to the system, and there may be a work of W1 to 2, maybe 80 kilojoules work done by the system, which is also a positive. Now coming to the 2 to 1 process along the path B, let there be Q rejected of 130 kilojoules along the path 2 to 1, which is a negative because heat is rejected. It should be taken as a negative sign. Then what would be the work in the process 2 to 1? That is the problem. So our aim is to calculate what is the W2 to 1 with the application of the first law of thermodynamics. First law says that cyclic integral of delta Q is cyclic integral of delta W. We have to add up all the heat transfers algebraically, that is plus Q1 to 2 plus of minus Q2 to 1 should be equal to the plus 1 to 2 because work is done by the system in the process 1 to 2 plus W2 to 1. Putting the values, plus 100 plus of minus 130 should be equal to plus 80 plus W2 to 1. It results in W2 to 1 is equal to 100 minus 130 minus 80. The answer would be 100 minus 210. It becomes minus 110 kilojoules. Minus sign shows that W2 to 1 is done on the system, like compression work. From this example, it should be understood that whatever the quantity unknown for which don't give this sign, based on the answer obtained, whether positive or negative, it can be decided whether work is done on the system or work done by the system. In the problem, if answer for the work 2 to 1 is obtained positive, then it would mean that work is done by the system. But here the answer is obtained negative. It means work is done on the system. Then coming to the second module, first law of thermodynamics applied to closed system in a non-cyclic process. Consider a closed system, that is a gas entrapped in a piston cylinder arrangement. Let there be heat supplied to the system of amount 100 kilojoules. This heat should be treated as positive because heat is supplied to the system. And let there be work done by the system, which is treated as positive. Let it be 70 kilojoules of work done by the system on the surroundings. Then, according to the first law of thermodynamics, Q1 to 2 minus W1 to 2 should be equal to the U2 minus U1, that is change in internal energy of system. In this example, 100 kilojoules of heat supplied and 70 kilojoules of work is done. by the system, which means the remaining 30 kilojoules of heat should have been used by the gas for increasing its internal energy. Substituting the numericals, we get plus 100 minus of plus 70 should be equal to plus 30 kilojoules, which indicates it is increase in internal energy of gas or system. In the differential terms, first law in differential form can be written as delta Q minus delta W is equal to du, where delta Q is differential amount of heat supplied in a differential change of state or infinitesimally small change of state undergone by the system. Delta W is equal to differential amount of work done by system in infinitesimal change of state, and du is differential change in internal energy of system. Now let me define internal energy as a property of thermodynamic system. It is an extensive property of a thermodynamic system which is defined as the sum of all the forms of energies like potential, kinetic, rotational, and vibrational forms of all the molecules contained in the gaseous system. U, which is a symbol for internal energy, should be measured in kilojoules. When capital U, which is the total internal energy, is defined mass of the gas, we get specific internal energy of the system in kilojoule per kg. The change in internal energy of a system between any two given end states shall be the same for all the paths followed between those two states. As we have seen in this figure, the change delta U along path A between state 1 and state 2 should be equal to change in internal energy along path B between same states, that is 1 and 2, because internal energy is a property. The change in a property, thermodynamic property, between two given end states shall be same for all thermodynamic paths followed between those two states. Now let us state Joule's law of ideal gas or perfect gas. The law states that internal energy of an ideal gas is dependent only on the temperature of gas. Mathematically, U is a function of T only for ideal gas. If temperature of ideal gas is constant, it implies internal energy is also constant. For real gas, which does not obey PV is equal to mRT at all pressures and temperatures, internal energy of real gas depends both on temperature of gas and also on the pressure. Now let us apply first law of thermodynamics for a non-cyclic process to various thermodynamic processes. Very first process what we consider is constant volume process, also known as Isochoric process. Consider a gas of mass m kg in a rigid vessel or rigid container. Let Q be the amount of heat supplied to the gas. The assumptions here are: number one, working fluid is ideal gas like air. Number two, process is reversible or quasi-static. Number three, system is closed. Then writing the first law of thermodynamics to the closed system, Q minus W is equal to delta U, change in internal energy. But here work done is integral PdV is 0 since there is no change in volume. Volume is constant. From the definition of CV, heat supplied at constant volume is given as mCV delta T, where delta T is increase in temperature of gas. CV is specific heat at constant volume. Substituting in the above equation, we get mCV delta T is delta U. All the heat supplied is used in increasing the internal energy of gas. So heat supplied in a constant volume process is equal to change in internal energy of the gas. Writing the first law in differential form for the constant volume process, delta W is 0 since dV is 0. For unit mass of gas m1 kg, delta Q is CV dt, where dt is the differential increment in temperature. For differential heat supplied delta Q, CV dt is equal to du, implies CV is equal to du by dt. Hence, specific heat at constant volume of ideal gas is rate of change of internal energy of gas with respect to temperature. The process could be indicated on a temperature entropy diagram as a curve with a slope of T by CV. The process is indicated on a PV diagram as vertical line, where the Charles law could be applied as P2 by P1 is equal to T2 by T1, since volume being constant. Coming to the second process, that is constant pressure process, or which is also known as isobaric process. The gas should be considered in a piston cylinder arrangement, because while heating the gas, the pressure might increase. To keep the pressure constant, the gas must be allowed to expand. That is, it must be able to do work on the surroundings by pushing the piston upwards. Let m be the mass of the gas. Here also the assumptions are working fluid is ideal gas, process is assumed as reversible or quasi-static, and system is closed system. If Q is the amount of heat supplied in this constant pressure process to m kg of the mass of the gas, and if the delta T is the increase in temperature of the gas, then heat supplied in constant pressure process can be given as mCp delta T kilojoules, where Cp is the specific heat at constant pressure. Indicating the process on PV plane, it appears as a horizontal line because pressure is constant. The heating gives the arrow rightwards, the cooling will give the arrow left side. The heat supplied to the gas is given as mCp delta T, whereas the work done is calculated from integral PdV. Integral PdV is applicable for the quasi-static work or reversible work done by the closed system. P being constant, work is given as P into V2 minus V1 kilojoules, where P is in kilopascals and change in volume is in meter cube. This work incidentally is equal to the area of the 1 to 2 on the x-axis because the process is reversible or quasi-static. Writing the first law of thermodynamics in differential form, for unit mass of gas, that is 1 kg, delta Q minus delta W is equal to du. This is the first law applied to the closed system in a non-cyclic process. Delta Q is Cp into dt, where dt is the differential increment in temperature and delta Q is differential amount of heat supplied to the gas. Delta W is equal to PdV. This is the equation applicable for any reversible process undergone by closed system. Substituting in the first law, we get Cp dt is equal to du plus PdV. Now I add 0 to the equation right hand side. That 0 is replaced with VdP because since dP is 0 in this process because P is constant. Now right hand side writing du plus PdV plus VdP. PdV plus VdP can be written as differential of a PV. It results in differential of U plus PV. Right hand side, define a thermodynamic property called enthalpy of system as sum of internal energy plus flow energy. H is equal to U plus PV, whereas small h is total enthalpy defined by M, known as specific enthalpy, can be taken as specific internal energy plus flow work done per unit mass, U plus PV. So coming back to the first law, we get for a constant pressure process, Cp dt is differential increment in enthalpy. Hence Cp can be written as dH by dt. Rate of change of enthalpy with respect to temperature. That is the definition of specific heat at a constant pressure. Cp is defined as rate of change of enthalpy with respect to temperature of gas. For a finite change of state, heat supplied in a constant pressure process is given as mCp delta T is equal to delta H. So the bottom line is heat supplied in a constant pressure process is equal to increase in enthalpy of system. The process, the isobaric process on temperature entropy diagram, can be indicated as a curve with a slope dt by ds at constant pressure process is equal to T by Cp. From the above two processes, it can be seen that slope of constant volume process is greater than slope of constant pressure process because Cp is always greater than Cv. That is, T by Cv is greater than T by Cp. Coming to the third process known as constant temperature process or isothermal process. Considering a gas in a piston cylinder arrangement, because the system has to be closed without any mass transfer between the system and surroundings, heat is supplied to the gas. The work should be done by the gas because the temperature has to be maintained constant. The process could be seen on a PV plane as a curve between the initial state 1 and the final state 2. The equation of process is given as PV is equal to constant, that is P1 V1 is equal to P2 V2. P1 by P2 is equal to V2 by V1. It is a very special process among all the processes because it should proceed with infinite slowness to keep the temperature of the gas constant while supplying heat to the gas. The work done by system during isothermal process or constant temperature process is calculated from integral PdV between the limits 1 to 2, where P can be replaced with the constant by V dV because PV is equal to constant. It results in P1 V1 log V2 by V1. Ln means log base E, which can also be written as R into T1 log V2 by V1, which can also be written as RT1 into ln P1 by P2. So many kilojoule per kg, that is work done per unit mass of the gas. Writing the first law of thermodynamics to process, that is isothermal process, Q minus W is delta U. This is first law applied to any closed system for any thermodynamic process. Applying Jules' law, which states that U is a function of T. Here T is constant. That means internal energy is also constant, which means change in internal energy is 0. Hence, substituting in first law, Q minus W is 0. That is Q is equal to W. That is heat supplied to system in a isothermal process or constant temperature process is equal to work done by the system. Heat and work are equal in constant temperature process. The slope of this process on PV plane can be given as minus P by V. Minus sign indicates that in a constant temperature process, as P decreases, volume shall increase, as is seen from the diagram on PV plane.